Okay, so this one is a video on section 3.5 of Dummit and Foote, which is about and transposition, something like that. Okay, so first, a definition, a two-cycle SN is called transposition. I think I actually tend to always call them two cycles anyway. I shouldn't talk while I transposition. I think I tend to call them two cycle anyway, but some people will call them transpositions, so you might find it helpful to know that. And what I mean by a two cycle is like the permutation that just swaps two elements. So 1, 2 doesn't touch anyone else, or 5, 3 swaps 5 and 3 but doesn't touch any other element. Okay, and a fact that we discussed when we first talked about SN is that SN is generated by two cycles. See already. SN is generated by transpositions. And you don't even actually need all of the transpositions. It's enough, for example, to use only the transpositions 1, 2, 1, 3, 1, 4, 1, 5, etc. through 1n. That's enough to get all of the elements of SN. But, certainly if you have all the transpositions, then you can generate SN. And so as a consequence, every permutation sigma in SN can be written not uniquely as a product of two cycles, because SN is generated by the two cycles, and even though the decomposition or factorization into two cycles is not unique. So like I said, there's many different ways. What is unique, what depends only on sigma, is the parity of the number of transpositions in the factorization, or whatever you want to call it, is well defined. So if you can write, an element sigma as a product of two transpositions, you might also be able to write it as a product of 4 transpositions or 6 transpositions, but you never would be able to write it as a product of 3 transpositions or 5 transpositions. And, also the same thing for odd numbers, right? So if you can write an element sigma in SN as a product of 5 transpositions, you might be able to also write it as 3 transpositions or 7 transpositions or 11 transpositions, but you'll never be able to write it as a product of, 2, 4, 6, 8 transpositions. Like, that's well defined. The parity of the number of transpositions that you need, that is well defined and depends only on the element sigma that you're thinking about. So we define the sign of sigma to be -1 to the number of transpositions in a factorization of sigma. So like I said, right, this number is not well defined, but -1 to that number is well defined, because this will always be an even or an odd number, so you'll always get -1 or +1. Okay. Note in particular, note that if if sigma is a k-cycle, so, sigma is just number, and there's k of them, and no one else gets touched, so the elements like just go around in a circle going to the next one, then the sign of sigma is -1, k -1. This is the same k-cycle, which kind of makes sense. So sigma is a 2-cycle. It should be odd, right? Because it can be written as 1 2-cycle. Indeed, the sign of sigma is -1, 2, -1, -1. I guess I don't know why this is easier, but that's just -1. So, and you can do this, you can show this in general for a k-cycle, because actually, and maybe I shouldn't say this, I should just pause to figure this out, but it's getting late, tired, and I don't want to do this anymore. But I think it's a fact that if you have, like, say 1 3 4, you can write this as 1 3 1 4 or something like that. Let me see. That does, it's the other way around, but this does work. So 1 4 1 3. So here, right, if you do the composition, remembering that we're composing right to left here, so this would be 1 goes to 3. Yes, 1 goes to 3. And then 3 goes to 1, 1 goes to 4, so 3 goes to 4, and then 4 goes to 1, so that does the sort, and that finishes the cycle. So you see, in general, if you can always do this, right? So if you have 5 3, and you do 5 3 5 1 5 7, kind of, like this 5 7 takes care of the 5 7 here. But then if you want to know where 7 goes, like first you're like, okay, 7 goes to 5, and then 5 goes to 1, so that makes like 7 go to 1. So you can kind of see how you can build like any cycle that way, by just always being like, when you want to go from 1 to 3, like say that 1 goes to 3, you're in your transpositions, you're like 1 goes to 5 and then 5 goes to 3, because they follow each other in the composition order here. And so this tells you, right, so this is a 4-cycle, and I can write it as a product of 3 transpositions. So it's an odd element of Sn. I haven't defined that yet. So the sign of this element is -1, and this is a 4-cycle. And this is a 3-cycle, but I can write it with 2 transpositions, so its sign is +1. So the sign of 1 3 4 is +1, and the sign of 5 7 1 3 is -1. And so the word that I used, and I should define it officially, so we say sigma is even if the sign of sigma is 1, and sigma is odd if the sign of sigma is -1. So this can be a little confusing, right? Every cycle of even length is odd, and every cycle of odd length is even. So we really only use even and odd not to talk about the length of the cycle, but to talk about this notion of the sign. Like we just never talk about the parity of the length of the cycle as being odd or even, because it's too confusing, and that doesn't really come up that often. So proposition, as you might expect, the map, it's actually easy to prove. The map sign from Sn to ±1 is a group homomorphism. Why is that? Well, composition in Sn is just concatenation, right? If I want to do this, and then this, I just like put them next to each other. Like that's what it means. It means do this and then this. So if I count, right, how many transpositions I need to write this times this, I need 1, 2, 3, 4, 5. And it's a fact, right, that, let me switch, -1 to the A times -1 to the B is -1 to the A plus B. So the sign of the product, oh, well, let's do this. The sign of the product is here, and the sign of this one is this one, and the sign of this one is this one. And so you see that the sign of the first element times the sign of the other element is the sign of their product, just by this like simple property of exponents. And I just want to say something about the group plus or minus 1, because there was some confusion on one homework. When I say plus or minus 1, I mean the group isomorphic to C2. And here, the isomorphism is given. So if I think of C2 as, the group with 2 elements, like cyclic generated by G of order 2, then the map is -1 goes to G and 1 goes to 1 in C2, right? So this is, so plus or minus 1 is a group under multiplication here. Okay, it's not a group under addition, because if I add, sorry, I always forget when I get stuck in this mode. If I add -1 and 1, I get 0, and 0 is not here. So it's not a group under addition. It's a group under multiplication, because -1 times -1 is 1, and 1 times 1 is 1. So that works. Okay, and now we finally get to the definition. Definition, AN called the alternating group on N symbols is the kernel of sign from Sn plus or minus 1. So we know that the kernel of any group homomorphism, is always a subgroup. So AN is a group, and actually the kernel is always normal. So AN is a normal subgroup in Sn, and sign is surjective because say 1, 2 goes to -1, right? That's an odd element, so something goes to -1, and sign is surjective, so Sn mod AN is isomorphic to C2, and in particular, the index of AN in Sn is just 2. And another reason, right, we kind of mentioned it before, so AN is non-abelian and simple, and in particular not solvable. We talked about that, how a simple non-abelian group is simple if n is greater than or equal to 5. The lower numbers are just kind of silly, so A1, that's just 1, A2, that's also just 1, A3, that's a group of order 3. There's only one group of order 3, so that's C3. So that's just in S3, the 3 cycle, the other 3 cycle, and the identity, and A4. So I'm like figuring this out on the fly, right? So the cardinality of S4 is 4 factorial, which is 4. So the size of A4 is 12, and there's more than one subgroup of order 12, more than one group of order 12. But actually, I think that this one is also non-abelian because it contains 2 3 cycles that have overlapping elements, right? Like it contains 1 2 3 and 2 3 4, for example, and these 2 don't commute, so it's not abelian. But it's actually it's not simple. So those are fun facts. And that's all I really want to say at this juncture about the sign and transpositions, the alternating group. But I am sure that as we learn more things, they'll come up again.